My name is Zephyr, this is my partner Omar, and today we're going to be discussing bias in AI systems.
So what was the original promise of using AI? It was to completely eliminate human bias, right? Computers don't have feelings, they don't have prejudices, and they rely completely on math to make their predictions. But the problem is the data that we're giving it to train is inherently biased because of society or any other reason. So this algorithm is not going to be any better than the data that we give it.
For some context, here's an actual case study from an Amazon algorithm that was meant to assess the quality of resumes. And because of the disparity between gender, with tech being a very male-dominated field, the algorithm, in order to optimize accuracy, would actually penalize resumes that were women's, that had words like women's or graduated from all women's colleges.
Okay, so to understand how to fix this, we created our own baseline model and trained it on adult income data sets. And we found that, we got a total 85.5% accuracy in predicting high income, which sounds good. It also exhibited a 21.39% demographic parity gap based on race and 17.84 based on gender. But it's objectively flawed. So where in the pipeline do we need to implement our mitigation solution?
So we've developed two options for mitigating the bias in these systems. First of all is pre-processing, which happens before we input the data into the model. And essentially we're trying to synthetically engineer the data set to not reflect these societal differences and have lower disparity between the different demographic groups. And option two is in-processing, where we're actually altering the training loop of the model in order to penalize it for relying on biased predictions and unfair patterns.
So viewpoint A basically says, by fixing bias within the training data, the model will naturally make predictions that are both accurate and fair. So the root cause is that algorithms aren't inherently biased. It's the data that we're giving it that's biased. And subgroup disparities are often caused by a lack of data, or the data isn't good quality, it's not representative of that group. Who should be fixing this inherent problem? We need data engineers and sociologists and domain experts who can effectively monitor data collection. And forcing artificial regulatory constraints onto algorithms does not solve the problem. So instead of penalizing the model, what we did was implement SMOTE, which stands for Synthetic Minority Oversampling Technique, into Model A. And what this essentially does is it synthetically creates new data points that are designed to equalize the different groups and their data so that they are all equally represented. By giving the algorithm fair, balanced data, we hope that it will have a more accurate and less biased prediction. So the effectiveness, we saw that, it got the highest overall F1 score out of the entire study with a 68.25% score. And additionally, it also got a massive spike in recall from 61.67 to 85.14. That basically means that the model was successful in identifying many more high income earners than what the baseline overlooked. And we were also able to reduce mistakes made, seeing how the equalized odds for race dropped from 66.67 to 55.56.
So viewpoint B essentially says that algorithms must be designed to intentionally undo the effects of real-world bias and correlations. So the root cause in this argument is that perfect data does not exist in the real world, and that subgroup disparities don't just appear because of missing data. Disparities appear when standard features are acting as hidden proxies for more sensitive features that the dataset might not have access to, but it can infer using other attributes. So standard algorithms find these, use them to maximize accuracy, but in turn make very biased decisions and latch onto these unfair patterns. So who should fix this? Fixing bias requires policies and regulations. These models need to be heavily monitored, and they need to be robust and accurate enough so that the historical data, regardless of how flawed it is, does not affect the bias of the outcome. So the mitigation technique here, as we said, is in processing. So we're altering the model's training loop, and we're using a fair learn constraint called an exponentiated gradient, which essentially is adding an auditing stage to the training loop. So every time the algorithm tries to use an unfair connection or a biased proxy to maximize its accuracy, the algorithm adds an exponentially growing penalty. So every time it ignores this penalty, it grows further and further until the model is forced to make more fair connections. So the algorithm must be structurally restricted so that it never learns these historical discriminations. So the effectiveness of this is that Model B virtually eliminated systemic bias in the data. The demographic parity gap for gender was brought from 17.84% to 1.32%. And even without being the main target, it actually brought down the equalized odds gap for race. It brought it down from 66.67% to 35.22%. And the cost of this is that the trade-off is that the F1 score dropped from 67.25 to 60.82. However, this is actually a promising result and is completely expected, because as we're removing the mathematical advantages for these privileged groups, there is going to be an inherent drop in accuracy. But this is necessary in order to break down and untangle these biased proxies.
All right, so mathematical models are created to recreate patterns, right? So if a model's accuracy is failing for a specific group, that means that there's a fundamental problem with the data. You can see figure 1, which we showed earlier. There is a huge disparity between males and females in big tech organizations. And this was, the model that Amazon used was a great example of how that can affect a model's output. We cannot expect the algorithm to make fair decisions if we're giving it bad data. So what's the solution to this? We have to change the data. We have to make it more fair for all the groups.
I see your point. However, the reality is that perfect data is not realistic in actual applications of machine learning, because there are always going to be, with these models being very good at predicting patterns and picking up on very intricate patterns in order to maximize accuracy, there's always going to be a way for these models to pick up on kind of unfair patterns and use that to maximize accuracy, even though it is inherently recreating the bias that we're trying to mitigate. For example, we can take a look at this. This is a chart of height and weight between male and female subjects. If the model had access to this, but did not have access to the actual gender of the participant, it would still be able to infer the gender and in turn would make the same biased predictions that it would if it were able to tell if the subject was a male or a female. So this is a proxy variable, and it allows the algorithm to recreate exactly what we are trying to avoid.
Taking a look at figures 3 and 4, we see the performance metrics by sensitive attributes, both sex and race, for the baseline model on the top and model A at the bottom. And as we discussed earlier, we can see that there's a huge increase in the recall score and a pretty good increase in the F1 score. And this is seen both in the sex representation and the race representation. And I mean, this is what we want to see. This is how we know that the model is making better predictions based off of the synthesized data.
The problem is that recall and F1 scores is not necessarily a measure of mitigating bias. It's just a measure of accuracy. And you can see the patterns are the same. And when we look at the male and female graphs, where female is higher than male in your model, the patterns are consistent. However, if we take a look at the data from the exponentiating gradient, you can see that it's actually making an effort to reverse these patterns. And where females are higher, males are actually higher in my predictions. So while it might not be as accurate, might have lower accuracy scores, it's actually actively mitigating the bias and reducing these patterns. And we can see this in the demographic parity difference for sex and the equalized odds difference for race. You see, with your model, it brought up the demographic parity difference, but with my model, it virtually eliminated it. And the same thing here. With my model, the equalized odds for race goes down significantly.
But you can also see that for the equalized odds difference in sex, that your model actually increased your model had the most equalized odds difference as opposed to mine and the baseline. So you can't really argue that this is applicable across all groups. So in summary, viewpoint A, in viewpoint A, pre-processing the data showed an overall increase in recall and F1 score. And conversely, there was an overall decrease in accuracy and precision. Pre-processing was good at pushing out correct predictions, but failed to effectively eliminate bias.
On the other hand, with viewpoint B, constraining the model did lead to a decrease in all the overall performance metrics, but there was an improvement across the board on 3 out of 4 of the tested bias metrics. So reducing the bias in the outputs, which was our overall goal, was achieved at the cost of a lower accuracy for the model's predictions. So to conclude, viewpoint B, model B, with exponentiated gradient was more effective at actually mitigating the bias, even though it comes at the cost of slightly less accuracy. Thank you.